Hello, Chemistry 12. This is Mr. Chan. And today what I wanted to do was I wanted to talk about standard reduction potentials. Now, we talked about oxidation and reduction in last day's lesson. And recall when we talked about oxidation reduction, what we have is a species that undergoes oxidation and a species that undergoes reduction. Now, one thing for you to be aware of is that not every substance oxidizes or reduces to the same degree. So looking at the standard reduction potential table, one can see which substances reduce easily while others do not. Now, in your data booklet, what you have is you have this standard reduction potential table. Okay, now, if you take a look, it actually is very similar to what you have for the acid-base chart. So in the acid-base chart, if we were to look at the data table, okay, so what we have is we have a acid on the left, base on the right, and you have a ranking going from the bottom left to all the way to the upper left. The acid gets stronger, going from right-hand side, upper right, down to bottom right, the base gets stronger. So how you read this standard reduction potential table is exactly the same. But instead of talking about acids or bases, we talk about oxidizing agents and reducing agents. Now, remember, when we talk about oxidizing agents, we're talking about the species that get reduced. And what we do is we read it from left to right. And reducing agents is ones that are substances that get oxidized. And on this particular table, we read from right to left. So reduced, species that are getting reduced, you read from left to right. Species that are getting oxidized, read from right to left. Okay, now, when we take a look at the standard reduction potential table, most easily reduced is found generally on the upper left of the table. Okay, and most easily oxidized would be found on the lower right. Of the table. Okay, now, so when you take a look at this table, you should notice some similarities. So the species on the upper left tend to undergo reduction because they gain electrons. Species on the lower right tend to undergo oxidation because when you read from right to left, they are producing electrons. And one thing that you should notice is this. If you take a look at the black lines again, you notice the stronger the oxidizing agent or stronger the substance to be reduced, the weaker it is to be oxidized. So what you have is fluorine, F2 is very good at reducing, F-1 is very weak at oxidizing. So again, if it's a strong oxidizing agent, it's a weak reducing agent. Just like if it's a strong acid, it is a weak conjugate base. Okay, so how you read this table is very similar to how you read your acid-base chart. Now, when we take a look at this, each reaction on the table can go either forwards or backwards. So let's say we have zinc solid in a solution of zinc 2 plus. So what we have is we would have for reduction, zinc plus 2 electrons and gets you zinc solid. Okay, and for oxidation, what you have is you have the zinc gives you the zinc plus 2 and 2 electrons. Okay, now So depending on how you read the table. So in this case, you are reading from left to right on the table. And the other case here is you are reading from right to left on the table. Okay. Now, when referring to an isolated half reaction, we use equilibrium arrows to show that the reaction can go either in the forward or backward direction. So if we were to just say the half reaction of zinc, we would just say, so let's say we had a half reaction, and I don't specify if it's oxidation or reduction. So I would write zinc plus 2 electrons would be in equilibrium with zinc solid. Okay, notice here I use the equilibrium arrow. But if the half reaction is made to undergo either reduction or oxidation as a result of being part of a redox, then we use a one-way arrow. So for example, if I said the reduction of zinc ions, then what I would put is I would put zinc plus 2 and 2 electrons gives you zinc solid. And notice here, I use a single arrow. Okay. Now, using the standard reduction potential table, we can tell if a redox reaction will occur and what will happen. In other words, which one gets reduced and which one gets oxidized in a redox reaction. Now, let's say there's two half reactions. Let's say we have a zinc in a solution of zinc 2 plus and copper in a solution of copper 2 plus. What will happen if we mix the two together? Now, first of all, one thing I want to emphasize is when I say zinc 2 plus, you're talking about a zinc solution. So something like, I don't know, something safe would be like zinc nitrate solution, AQ. Okay. So what you have is you have the zinc ions and a zinc solid, right? But the +2 ions are neutralized by a negative ion. Okay, same idea with the copper 2 plus. So it says in a solution of copper 2 plus, instinctively think of something like copper 2 nitrate or copper 2 sulfate, something with a positive and negative ion. So what do I mean by this particular scenario? So let's say if I had a solution here, let's say we have my zinc solid and I have my zinc ions, and I slap it together with, let's say, a beaker full of copper ions and copper solid. So what will happen when I mix these two, this combination together? Okay, so it's like that. So first of all, we look for zinc 2 plus and copper 2 plus on the table. Since copper 2 plus is higher up on the left, therefore it is more easily reduced. So what do I mean by this? So if we look at our standard reduction potential table, what you have is you have copper 2 plus up here, and you have zinc 2 plus down here. In this case, if you compare these two, copper +2 is better at reducing. Okay, it's very similar to when we compare the strength of acids, of two acids, or when we compare the strengths of two bases. So in this case, we're comparing the two ions. Which one is better at reducing? Oops, I want to say I made a mistake here. It should be the copper +2 up here. What's the difference is because of the electrons. Okay, so I'm looking at this particular half reaction here and this particular half reaction down here. Okay, now in this particular case, so what happens is copper will undergo reduction. So we have Cu plus 2 and 2 electrons will give you Cu solid. Now, if we look at zinc metal and copper metal on the table, we see that zinc metal is lower on the right-hand side, therefore more easily oxidized. Again, if we take a look here, if we compare the copper versus the zinc, in this case, because copper solid is weaker at undergoing oxidation than zinc, notice zinc is lower down on the right-hand side, so it's stronger. So therefore, zinc solid tends to oxidize. So in this particular case, if we were to write this out, we would have zinc solid would give you zinc plus 2 and 2 electrons. Now, this step that I did with the zinc is actually kind of redundant. The reason being is because if copper 2 plus is better at reducing, basically the zinc has no other option except to oxidize. Okay, so that's something that you could think of. So step C, where I look at zinc and copper on the table, it's kind of a redundant process, because if I know that copper 2 plus ions is better at reducing, then the zinc must be better at oxidizing. So when we balance the charges, what we get is we get copper plus 2 plus zinc solid gives you copper solid and zinc plus 2 ions. Okay. Now, remember, you need an oxidation half reaction and a reduction half reaction to have a redox reaction. Okay, you need one that undergoes oxidation, the other undergoing reduction. Now, if you were only given 2 potential reactants, you have to check the table to see what happens. Let's say both reactants were found on one side of the table. So let's say you were only given a piece of copper solid. Okay, so if I had here a piece of copper solid and I slapped on a piece of zinc solid, what would happen? In this case, there would be no reaction because both solids undergo oxidation. Okay. If you take a look at the copper solid and the zinc solid on the standard reduction potential chart, you will be noticing both of them are found on the right-hand side. So both of them undergo oxidation only. Okay. Now, if one reactant is found on the left and the other is found on the right, it depends on location. If oxidation is lower right and reduction is upper left, the reaction is considered spontaneous or the reaction occurs. Now, what do I mean by this? Well, let me give you a classic example here. So let's say we had Mg solid and HCl. Okay. Now, you folks have done this when we talk about chemical change in grade 9, grade 10, grade 11. And what you get is you always, all of you know, single replacement reaction. So you get MgCl2, AQ. Let's see, let me just write that out. And H2 gas. Now, how can we explain it using the standard reduction potential table? Well, what we do is we take a look here. So magnesium is found, where do we find this? This is found on the lower right-hand side. Okay, so if we take a look at our standard reduction potential table, we have magnesium, which is right here. Okay, now, how about hydrogen? How about HCl? Well, going back to acid bases, HCl is here a source of H plus. And this is found on the upper left. Okay, if we look at the chart here, okay, we have H plus right here. So because you have reduction on the upper left, oxidation on lower right, what we get is we get a reaction. So here, we get a spontaneous reaction. So this is why we get hydrogen gas being produced. All right. Now, this occurs for single replacement reactions. Now, what if reduction is lower left and oxidation is upper right? What you get is you get no reaction or is non-spontaneous. Now, for some of you who've taken electronics, you will be familiar with this reaction. So let's say we have copper solid and hydrochloric acid. Now, when you're making circuit boards, what happens is it's very common to clean copper circuit boards with hydrochloric acid because the copper doesn't react with the hydrochloric acid, but the hydrochloric acid sort of cleans off all the impurities. Now, in this particular case, we get no reaction. Now, again, why is it? Is because if we look at the location of copper solid and H plus, so if we look at our standard reduction potential table, we have H plus, which is right here. We've talked about it already. And notice the location of copper solid right here. Okay. Now, because copper solid is upper right and the H plus is lower left, you have no reaction. So in this case, the copper solid here is upper right. And again, HCl is a source of H plus. Which is lower left. This is why we have no reaction or non-spontaneous. Okay. So when we take a look at a reaction and see if it works, we have to take a look at, for redox reaction, location. Is one found on the right, one found on the left? And is it upper right, lower right, and so on? Okay, so you have to sort of take a look at where the location is of the two species undergoing oxidation and reduction. Now, some of you may say, well, this is totally new to us. And the answer is not. You've actually seen this before. Okay, now notice I'm using single replacement reactions. Back in Chem 11, if you remember chemical reactions and we did single replacement, remember we talked about the activity series. Okay, remember we said that, let's say for magnesium and HCl, magnesium had to be higher up, the more active element would replace the lower element. So notice in this case, magnesium was higher than hydrogen, and that's why you got MgCl2 and hydrogen gas. So this activity series was actually very similar to your standard reduction potential table that we have, that I introduced for you today. Okay. Now, a couple of things for you to be aware of. A lot of these reactions are very straightforward. So let's say, gold here or chlorine, but you will notice that some of these reactions, notice that there's H plus in there. Okay, they are acidified. Okay, so these will only work in an acid solution, and that's why you need the H plus. Some of them will work regardless, but for some with the H plus in the equation, they need to have an acidified, an acid in an acidified solution. All right, ladies and gentlemen. So this is why when you take a look on the back of your notes, if you take a look at some of the answers, it says reduction with H plus or reduction with H plus is because they need to be in an acidified solution for it to react. All right, ladies and gentlemen, thank you very much. Have a good day. Bye-bye.